Okay, so the next function that we'll graph here is f of x equal the square root of x plus 4. If x is negative 4, and by the way, I can't plug in anything less than negative 4, so I know that the graph is going to start at negative 4, and anything bigger than negative 4 is going to be okay to use here. If x is negative 4, I get 0. If x is negative 3, I get 1. If x is 0, try to use nice numbers, I get the square root of 4, which is 2. And if x is 5, I get the square root of 9, which is 3. Okay, so what's happening here is I'm looking at a half of a parabola on its side, starting at negative 4, 0, and heading upward and outward towards the right. Make sure that there's an arrow on the right side. The domain of f is the set of all x such that x is greater than or equal to negative 4. And that we already said because negative 4 is the first number that we're using, and can't have anything less than that. The range is the set of all y such that y is greater than or equal to 0. The range, if I look at the y-axis and above and below, anything that is 0 or bigger is going to, when I look to the left and the right, that's going to put me on the graph. So set of all y such that y is greater than or equal to 0. Okay, if it's possible to solve an equation of a y in terms of x, we write y equal f of x, and we say that f is given explicitly. An equation in implicit form when it is in implicit form when it is not in explicit form. So here's some examples. I've got an equation written in implicit form and then rewritten in explicit form. The first one, 2x plus y equals 3, is in implicit form. The reason is because the equation has been solved, has not been solved for y, but now it has been by subtracting 2x from both sides. And when you solve for y, y and f of x mean the same thing. So I could use function notation if I wanted to. I'd call this f of x or g of x or whatever. On the second one, if I add y and subtract x, then y is equal to x squared minus x. Y and f of x mean the same thing. So because they are the same, I can say f of x is equal to x squared minus 6. On the third one, divide by x, y is equal to 3 over x. Y is equal to 3 over x. Y and f of x mean the same thing. So f of x is equal to 3 over x. Now, not all equations define a function y equal f of x. If an equation is solved for y and more than one y value is obtained, then the equation does not define a function. Okay, so for example, is the equation x squared plus y squared equals 1 a function of x? What type of an equation is this? This is a circle centered at 0, 0. So we talked about the equation of a circle the other day. The equation of a circle is in standard form is x minus h squared plus y minus k squared equals r squared. The fact that h and k are both 0 and r is 1 means that this is a circle centered at the origin of radius 1. Okay, well, if I solve this equation for y, because right now it's not solved for anything other than 1, but if I solve for y squared is equal to x squared minus 1, or 1 minus x squared, sorry. And then when I take the square root of both sides to get y all by itself, y is equal to the square root, plus or minus, the square root of 1 minus x squared. So this would not be a function, because for anything less than 0, actually, if we were to let x be 0, then y would be 1 or negative 1. Okay, and let's just check that. If x is 0, y is equal to positive 1 and y equals negative 1. So 0, 1 and 0, negative 1 are on the graph. Well, hold on. I thought for each x there's exactly one y, not two different y's. So that's where the problem is. We'd have a x 0, 1, and 0, negative 1. Not a function. In general, circles are not functions because every time you're going to have an equation where there's a y squared term, and so at the end of the calculation you're going to take the square root of both sides, and having to deal with this plus minus situation like what we have here. So a circle is not a function. Okay. Probably something you've heard before, the vertical line test. If a vertical line intersects a graph and at most one point, then the graph is a function. So here's a graph of some curve that would be a function. Notice how anywhere I draw a vertical line, the graph of a vertical line would intersect in at most one point, anywhere, and so therefore this graph would be a function. Okay, over here in this example, this is not a function. I've got a parabola that's on its side, and the parabola fails the vertical line test. So this is not a function. Now, keep in mind what the theorem says. It says that if every vertical line intersects the graph and at most one point, then the graph is a function. Okay, so we're all good on the right side of the y-axis, but where the theorem fails is we're all good on the left side. Excuse me. But where the theorem fails is once we get over the right side. If I draw any vertical line on the right side of the graph, it's going to intersect at 2 points that I can see here. So this would not be a function. Also, circles are not functions. If I were to draw a circle anywhere and use the vertical line test, a vertical line drawn anywhere, would intersect a circle at more than 1 point, and therefore not a function. Okay, so these are some typical graphs of ones that would not be functions and ones that would be functions. Make sure that you know that for the quiz and the test. The homework is on page 44, problems 1 through 141. Be sure that you look at those for me. Okay.